In this video, we're going to talk about computing beam deflections using the double integration method. So in a previous video, we established the differential equation that defines the relationship between moment and curvature. So that is this equation, which says the second derivative of the transverse displacement with respect to x, which is also the curvature, is equal to m over EI. M is the bending moment in the segment, E is the elastic modulus, I is the moment of inertia. Another way we can write this is that the first derivative of the rotation is equal to m over EI, right? Because we know that theta is equal to dV dx. Now, once we express the moment as a function of the position along the length of the beam, then successive integrations of this equation will result in the beam's slope and deflection, right? So we established that theta is equal to dV dx, right? So that means if we integrate the moment function over EI with respect to x, that would give us the slope of the beam, right? So that would give us a function for the slope of the beam. And then if we do another integration, that will give us the transverse deflection or the vertical deflection in the beam. Now, for each of these integrations, a constant is going to be introduced, and this constant has to be solved, or these constants need to be solved to obtain a unique solution. And we'll see how that plays out in another video where we will implement the double integration method in an example. Now, these constants of integration, the way we determine them is that we evaluate the deflection or slope functions at points where the values are known. These are called boundary conditions. So for example, if you are at a roller or a pin support, we know that the deflection is going to be 0. Similarly, if we're at a fixed support, we know that the deflection is 0, but we also know that the slope is going to be 0. In addition to the case of boundary conditions, we can also use continuity conditions to solve for the constants of integration. So to illustrate these continuity conditions, we will look at a beam that's loaded with a point load. It has some deflection. And we will say that the distance from the left end to the point load is A, the distance from the right end to the point load is B, and the transverse deflection, we'll call that B. And so this beam, if we look at the bending moment diagram for this beam, it's going to look something like this, where there are two moment functions for the two different parts of the beam. So the part to the left of the concentrated load has its own moment function. The part to the right has its own moment function. Right, so what we can do is we can use, say, for example, x1 to define the moment function on the left, to the left of the point load, and we can use x2 to define the moment function to the right of the point load. And at the point where the two moment functions intersect, which is at the location of the point load, the two moment functions must give the same deflection and slope. So let's call this point, B, right? So that's at the location of the point load. Then that means that at B, the deflection, let's say the deflection that we obtain from the moment function to the left must be equal to the deflection that we obtain from the moment function to the right of the point load. Similarly, at B, the rotation that we obtain from the moment function to the left of B must be the same as the rotation we obtain from the moment function to the right of B, right? So we refer to these again as continuity conditions, and we can use these continuity conditions to solve for the constants of integration. So in the next video, we're going to see how this plays out in an example.